Okay, today we will work on an example problem, and while working on it, we will try to remember what we learned last year on the stiffness method. So it will be a simple frame. So a frame like that. We have a fixed boundary condition here, fixed boundary condition here. This length is 8 meters. The height of the frame is 4 meters. We have a uniformly distributed load on it, and the magnitude is 12 kilonewton meters. And let's add a point load here. And the magnitude of that point load is 10 kilonewtons. So let's try to analyze this frame by using the stiffness method. Now the first method is we no longer work on the whole structure, we do discretization. So wherever we see a discontinuity, we have to add a nodal point. So if I show the nodal points on the structure, these are the nodal points. Remember that these are our solution points in this structure. So the discrete version is as follows. So I have a node here, a member between two nodes, another node, member, node, also a member, and a node. So let's show the nodes like that. Let me mention one thing. To simplify the solution, we will assume axial rigidity in the members. So in this, which means that we are ignoring the axial deformations. So in this structure, what I see is I see 4 nodes and I see 3 members now. Now let's go node by node and determine the degrees of freedom at each node. So let me give some labels so that we can better communicate. So A, B, C, D. So at point A, we have a fixed support. So all the degrees of freedoms are equal to 0. Now let's come to point B. Can it move in the upward direction? The answer is no, because the column is rigid. It cannot deform axially. Can it move in the horizontal direction? The answer is yes. So let's put a degrees of freedom here. Sorry, I erased this one. So let's put a degrees of freedom. Let's call it D1. Can point B rotate? The answer is yes. So that's our second degrees of freedom. Now let's jump to node C. Can it translate in the horizontal direction? The answer is yes. How much? It will be the same as point B, so I'm giving the same degrees of freedom here. That's D1. Can it rotate? The answer is yes. That's D3. Can it move in the upward direction? The answer is no, because member CD cannot elongate. And point D, fixed support, no degrees of freedom. So basically in the structure, I have 3 degrees of freedom. So I need 3 equilibrium equation. Now, in the solution method, we are separating the external actions. We are describing the external actions with the force vector. And the response to these external actions is defined by the stiffness matrix. So let's first calculate the force vector. Remember that in order to calculate the force vector, we are doing a superposition. So this is our original structure. I'll just draw it a little bit smaller. That's the original structure. Sorry for the scale. This is the loading on it. And this is a deformable and subjected to member loads, right? So we are investigating the structure in 2 parts. The first part, we say no nodal deformation. Okay? So how do we show no nodal deformation? By fixing the ends of the members. So we are trying to figure out what will happen if we don't have any deformation in the system. And remember that each of these members are kinematically determinate members. Okay, we have kinematically determinate members, and let's show the uniform distributed load on it. So which is 12 kilonewton per meter. Since this is a kinematically determinate structure, I can actually calculate all the end forces, and I can calculate the end forces by using the fixed end moments and forces. So when you do calculate it, this is 64 kilonewton meters. That's the moment. I have another moment here again, that's 64 kilonewton meters. So this is the picture when we have no nodal deformation, and if you transfer these forces to the nodes, you see this structure is not in equilibrium, which means that the structure should deform in such a way that it will balance these two unbalanced forces plus this point load. So the second case is when we have only nodal deformations. What causes the nodal deformations is the unbalanced forces. In other words, the structure should deform in such a way that the internal forces created due to deformations should balance the unbalanced nodal forces. So we have 64 kilonewton force here, so I should have the same but the opposite force here, same but the opposite force here, so that when I add only deformation case with the no deformation case, these two moments will balance each other. So I got 64 kilonewton meters here, 64 kilonewton meters here, and I have an unbalanced nodal force that's equal to 10. So by looking at this figure, I will determine the force vector. In other words, the force vector shows the unbalanced nodal forces. So what is the first load? That corresponds to the first degrees of freedom. This is my first degrees of freedom. I got 10 here. They are in the same direction. So this is plus 10. The second degrees of freedom is D2. Counterclockwise is positive. So I have 64 here. It's clockwise. So that's why the second is 64. The third degrees of freedom is counterclockwise rotation, and the corresponding unbalanced force is 64 in the same direction. So I got 64 here. So this is the force vector. Now let's continue. Let's try to determine the stiffness matrix. So our starting point is this. Now, this is the frame, and we are saying that this frame has 3 degrees of freedoms. We got D1, D2, and D3, and I can represent the deformed shape of this structure with these 3 degrees of freedoms. Here I'm saying that the total deformed shape is equal to case 1, deformation due to D1 only. So I don't know what the magnitude of D1, but let's sketch So due to D1, we expect to see a deformation as follows. So we have only D1. That's the deformation caused by D1 only. The rest, D2 and D3, is equal to 0. So let's put a note. This is only D1. D2 and D3, they are equal to 0. Of course, this is not the total deformed shape of the structure, plus case 2, where we have D2 only. So let's again sketch the deformed shape. So in that case, I should have D2 only. So that's D2. The rest should be equal to 0. So in that second case, I have only D2. D1 is equal to D3, that's equal to 0. Then plus case 3, as we expect, this is D3 only. So again, let's sketch the deformed shape. Now here we have D3 only, 0 rotation and no translation. And this rotation is equal to D3, and case 3 is so with this equality, we are saying that the total deformed shape of this structure is equal to deformation due to D1 plus deformation due to D2 plus deformation due to D3. So when you add these deformation, you obtain the final deformed state of the structure. So the deformation is caused by unbalanced forces, right? We said that in order to balance these forces, the structure should deform. So reverse, we can say that the D1, D2, and D3 will be due to the unbalanced forces. Now, in this, at the bottom, let's show the forces now. So this is again, now the structure. Let's show the unbalanced forces on this structure. So here I have 64, and 10. So these are the unbalanced forces, and we say that unbalanced forces should be balanced by resultant member forces due to deformation. Okay, so here we said that, okay, now for the first case, how much force do I need? Or how much force do I see when the member deforms in the following way? Okay, we have D1 only. So what are the internal forces due to that D1 deformation? So let's figure that out. So for that, let me draw the discrete version of the structure. Okay, so let's show the deformed shapes. So this is the deformed shape, and we know that this deformation, sorry, is equal to D1, and I don't see any deformation at this member. Okay, so I take a look at this member now. This is the deformed state. So how much forces do I see on this member? We do it by with the stiffness, the slope deflection equations. All right. So the shear force here, let me use a different color, is equal to 12 EI over 4 cubed. The length is 4. The rotation 6 EI over 4 squared, and I should always multiply them with D1. Okay, and the force here is again 6 EI over 4 squared times D1. Let's do the same thing here. 6 EI 4 squared times D1. 6 EI 4 squared times D1, and the shear force is 12 EI divided by 4 cubed times D1. So transfer these forces to the nodes. So I have this moment here, this shear force here, likewise a moment here, and a shear force here. But I need some additional forces here, right? In order to create this deformed shape, I have to apply K11 so that it will create a displacement that's equal to D1. So I have to have K12 here to keep the rotation equal to 0, and K13 here to keep the rotation equal to 0. Now, I have to write the nodal equilibrium equations. In order to do that, let me transfer this axial force to this node. So, if I write the equilibrium equations, the nodal equilibrium equations for this node, I obtain K11 as equal to 2 times 12 EI over 4 cubed multiplied by D1, so that's equal to 3 EI over 8 D1. So for K12, I'm writing the moment equilibrium equation for this node. Then K12 is equal to 6 EI over 4 squared D1, which gives me again 3 EI over 8 D1. And I'll do the same thing for K13, write the nodal equilibrium equation, and I obtain K13 as 3 EI over 8 D1. So these coefficients, what do they tell me? K11, K12, K13. Remember that in the case 1, I am trying to generate this deformed shape. Okay? In order to generate this deformed shape, I apply K11, K12, and K13. K11 creates a force that gives me D1 displacement, and K12 and K13 keep the other two rotations equal to 0. The magnitude of these forces are as follows. How do I obtain them? For each member, I looked at their deformed shape by using the slope deflection equations. I calculated the end forces. Then I transfer them to the nodes, write down the nodal equilibrium equations, and I obtain these coefficients. And then I'll repeat the same thing for the other cases. So for case 2, let me draw. And I'll do the same thing for case 3. Let me draw again the discrete version. And let me show the deformed shape for both cases. So for the second member, that's the deformed shape. For the first member, that's the deformed shape, and 0 deformation here. And this one, that's the deformed shape. For the third member, that's the deformed shape, all right? So in order to generate that deformed shape for the second case, I have to apply K22. K22 will create a rotation that's equal to D2. I have to apply K23 to keep the rotation equal to 0, and K21 to keep the translation equal to 0. The same logic in the third case also. I have to apply K33 to create a rotation that's equal to D3. Okay? Then K32 here and K31 here. All I need to do right now is take a look at these members, and for the deformed shapes that I drove here, I have to calculate the end forces. So again, slope deflection equation, this moment is 4EI over 4 multiplied by D2. This moment is 2EI over 4 multiplied by D2. And I need the shear force here, that's equal to 6EI over 16 multiplied by D2. So I'll do the same thing here on this member, 4EI over 8 D2, here 2EI over 8 D2. I don't need the shear forces on this member. Let's switch to the third case. This one is 2EI over 8 D3, 4EI, 4EI over 8 D3. The same coefficients here, 4EI over 4 D3, and the shear force, let me write it here, 6EI over 16 D3. Okay, so all we need to do then transfer these forces to the nodes. And so on, and write down the nodal equilibrium equations, and we obtain K21 as equal to 3 over 8, 3EI over 8 D2, K22 as equal to 4EI over 4 plus 4EI over 8 D2, which gives me 3EI over 2. And K23 is equal to 2EI over 8 D2, which is equal to EI over 4 D2. If you do the same thing, I'll just write down the answers. K31 is equal to 3EI over 8 D3. K32 is equal to EI over 4 D3. And K33 is equal to 3EI over 2 D3. So these are the total forces that is required to create this given deformed shapes. All right, now what do we do? Now take a look at, let me change the color of this. Now take a look at this equality. We have these pluses here. So let me write the equilibrium equations for this first case. So here we are saying that. Let's write the nodal equilibrium equations. So for this one, 10 is equal to K11 plus K21 plus K31. Right? So that's equal to 3 over EI over 8 times D1 plus 3EI over 8 times D2 plus 3EI over 8 times D3. So this is our first equilibrium equation. This is the shear equilibrium at node C. Now for the second equation, now I will use this one. I will write the nodal equilibrium. So 64 is equal to K12 plus K22 plus K23. So let's write that. Minus 64 is equal to K12 plus K22 plus K32, and that will be equal to 3EI over 8 times D1 plus 3EI over 2 times D2 plus EI over 4 times D3. And as you see, this is our second nodal equilibrium equation. That's the moment equilibrium at node B. And for the final equilibrium equation, I will write the nodal equilibrium for node C. So 64 is equal to K13 plus K23 plus K33 plus K23 plus K33, and this will give me 3EI over 8 times D1 plus EI over 4 times D2 plus 3EI over 3 times D3. And that's my third equilibrium equation. So as you see, we have three unknowns, D1, D2, and D3, and we got three equilibrium equations. If I solve the system of the equilibrium equations, I should be able to obtain the values of D1, D2, and D3. So if I write everything in matrix form, this is what we see. So on one side I have 10 minus 64, this is plus 64, that's equal to 3 over 8, 3 over 8, 3 over 8, 3 over 2, 1 over 4, 3 over 2, and that will be a symmetrical matrix. EI multiplied by D1, D2, and D3. So we are saying that that's the force vector, unbalanced force vector. Unbalanced force vector that causes deformation in the system is equal to, that's our stiffness matrix, we call it K multiplied with the unknown displacements U. So when we write the stiffness coefficients in the following way, they actually mean that, for example, this force is the force required to create a unit translation, right? This one is the moment required to create a unit rotation at node B. This one is the moment required to create a unit rotation at node C. So when I multiply it with translation, I get the total force due to that translation. So what about the off diagonals? This one, I have a unit translation. In order to keep the rotation equal to 0, that's the force I need. Likewise, I have a unit translation, and I want to keep the rotation at node C equal to 0. How much force do I need? This much. So that's the meaning of the stiffness matrix. And when you solve this system of equations, you will get the values of D1, D2, and D3. Of course, here what I did is I actually derived the stiffness method one more time. We don't do it this way, right? When we solve this problem, we don't generate the stiffness matrix like that. We have a simpler, more practical way of doing it. So let's very briefly visit that. So I'll just generate the stiffness matrix one more time. Just to remind you what was the procedure. So we are saying that case 1 is D1 is equal to 1, since these coefficients means a force that creates a unit translation. So we are giving the unit translation or the rotation to the structure, and D2, that's equal to D3 equal to 0. So again, we show the discrete version of the structure. I'll just show it the first, just for the first case. We are saying that that's unit translation. That's unit translation. And these are the stiffness coefficients. Now, by looking at this picture, again, you can either use the slope deflection equations, or remember that we already derived the element stiffness matrices, and from the element stiffness matrices, you get the coefficients that you are looking for and use them. So let's use the slope deflection equations again. So we know that these are the moments. And the shear component is this way. Actually, we are doing the same thing, right? We are drawing the same deformed shape one by one. We are transferring them to the nodes. And write down the equilibrium equations and obtain what K11, K12, and K13 is. Then we repeat case 2. This will give you the second row of stiffness matrix. And you do the same thing for case 3. That will give you the third row. So that's it. It doesn't matter what type of a structure we have, we always do the same thing. The first step is discretization. Now, in order to determine the unbalanced forces, we do superposition, right? So we are saying that the total loads on the structure is equal to the case when we have no nodal deformation plus the case when we have the only nodal deformation, and this part will give me the unbalanced forces. Now for the stiffness matrix, this part is just to show it to you, but for the stiffness matrix, in order to obtain K, we create our cases. We say case 1, D1 is equal to 2, rest is equal to 0. Draw the deformed shape and obtain these coefficients. Transfer them to the nodes and get your first row of the stiffness matrix. Repeat the same procedure for the other degrees of freedoms and obtain your final equilibrium equation. Of course, the analysis doesn't end here. The next step, once you determine the unknown displacements, you have to recover the member and forces. And this is the next topic that we will talk about.